Supermassive black holes containing millions or even billions of solar masses perplexingly reside at the heart of most massive galaxies. These gravitational beasts play a central role governing the growth of cosmic structures and galactic ecosystems over the 13.8 billion-year history of our universe. In this video, we'll explore leading theories explaining the origins of supermassive black holes. Learning how these energetic engines formed soon after the Big Bang provides keys for unlocking their intimate link with galaxies. We'll analyze how they generate extreme outbursts while voraciously feeding on gas and stars, sometimes glowing brighter than the total starlight of their host galaxies. Their role accelerating galaxy growth through feedback loops and regulating star formation rates is becoming increasingly clear. We'll also highlight mysteries remaining to be solved about their relationship with dark matter halos, orbital dance with dual black holes during galactic merger events, and whether their accretion disks can launch interstellar probes across vast distances. Join us on an epic adventure traversing the cosmos through space and time with science as our guide to illuminate the indispensable role of supermassive black holes shaping the large-scale structure of our amazing universe. Seeds of creation, the first black holes. What extraordinary sequence of events soon after the Big Bang could have led to the emergence of the very first black holes? Their origins represent one of the most perplexing mysteries of modern cosmology. Leading models rely on cataclysmic processes unfolding during the deaths of the earliest generation of stars lighting up the young cosmos. The primordial universe expanded and cooled rapidly in the aftermath of the initial cosmic explosion. Clouds of primordial elements gravitationally coalesced into the first stars within a few 100 million years. The population 3 stars marking cosmic dawn were real behemoths up to hundreds of times more massive than our Sun. Although their lifetimes measured just a few million years, hot blue stars fused elements rapidly in their cores. At the conclusion of such short and spectacular lives, simulations indicate population 3 stars likely collapsed violently as tremendously energetic hypernovae. The resulting explosive shockwaves visible across the universe signified the deaths of these pioneers, the very first cosmic lighthouses. Remaining at the core, black hole seeds perhaps up to 1,000 solar masses or higher would have formed. Emerging from the remnants of the first stars, these newborn black holes commenced accumulating the necessary billions of solar masses to become the supermassive objects we observe today. But how exactly did they manage to grow so exponentially vast over such relatively brief epochs of around 13 billion years? Runaway growth of black hole seeds. The current timeline fails to provide enough of a window for stellar mass black holes from population 3 stars to reach scales of billions solar masses through accretion of ambient matter alone. More elaborate mechanisms must have been involved to explain their hyper-acceleration expansion, particularly within the first billion years after the Big Bang. On their own, accretion rates based on gravitational capture of surrounding material would have taken too long. Even under sustained Eddington limited feeding, a 10 solar mass seed would require almost the entire 13.8 billion year history since the Big Bang to achieve scales of a billion solar masses. Researchers propose more dynamic scenarios in the unbridled environments of early galaxies for propelling their breakneck growth. Modern galaxies contain relatively modest amounts of gas and dust, limiting fuel accessible for accretion. But early galaxies were still coalescing into structures from dense interstellar medium, ripe feeding grounds for black holes positioned desirably at the centers of gravitational wells. Early galaxies essentially provided all-you-can-eat cosmic buffets. Abundant flows simply overwhelmed nascent black holes. Furthermore, abundant mergers between neighboring galaxies delivered additional infusions of fresh star-forming clouds and clusters. Tidal forces churned contents into active accretion disks which in turn boosted consumption rates. The galactic merging transient super-Eddington accretion scenario supports exponential black hole mass buildup over 500 million years after the Big Bang. Observational evidence confirms supermassive black holes already existed as early as 800 million years after the Big Bang, powering energetic quasars. Detecting earlier era signatures visible with next-generation instruments will further constrain models. But stellar mass seeds got assistance. Black hole outbursts and quasars. What transpires when a supermassive black hole really chows down, blazing through surrounding gas and dust reservoirs? The gravitational beast voraciously feeds on matter at astonishing rates for periods less than 1,000,000 years, unleashing some of the most brilliant cosmic fireworks, quasars. Escaping photons generated deep within the accretion disk and relativistic jets beam outwards, some eventually reaching telescopes billions of light-years across space-time. Analyzing properties of this ancient light provides precious glimpses into behavior of energetic supermassive black holes from even as early as 800 million years after the Big Bang. Quasars glow intensely across broad regions of the electromagnetic spectrum, but the prodigious visible light output often substantially outshines the total luminosity from all the stars contained within the entire galaxy. A quasar broadcasting with equal brilliance of a few 100 trillion suns can drown out its surrounding galaxy. What mechanisms enable quasars to blast out astonishing 100 to 1,000 times as much energy as the Milky Way? Hot gas violently circles inward, forming a swirling accretion disk which heats up immensely through gravitational potential energy and viscous friction forces. Before finally crossing the event horizon, tremendous magnetic fields launch some material along the rotational poles as defiance. These are the ultra-bright jets exceeding half-light speed. The variability timescales for some quasars imply emission regions very close to the central black hole. Quasar outbursts seem capable of outputting their extreme energy for a few million years before fading and transitioning through various intermediary phases back into quiescence. This cycle repeats on scales of tens of millions of years as surrounding gas clouds refuel the black hole for subsequent ignition events. Mapping the cosmological distribution of quasars reveals that their population peaked in number when the universe was 20% to 30% of current age at redshifts between 2 and 3 some 10 billion years ago. Earlier on, smaller galaxies contained actively growing yet less massive central black holes. After peak epoch, quasars faded in number as galaxies exhausted available matter and matured. This pattern highlights their intimate link with galaxies racing from chaotic youth into sedate middle age. Let's explore next how outbursts arising from these cosmic lighthouses profoundly influence galaxy morphology and star formation. Their brilliant signatures disclose hidden connections between galaxies and supermassive black holes engaging a gravitational tango across cosmic time. Galactic winds and jet-induced star formation. Supermassive black holes assert monumental influence over galaxies as their stellar nurseries and interstellar ecosystems respond to intense outbursts. Relativistic plasma jets piercing through gas clouds trigger star formation like a cattle rancher wielding a high-powered cattle prod. Meanwhile, violent winds ejected from accretion disks generate expanding bubbles clearing paths through stellar bulges. Observational relationships between galactic bulges and central black holes substantiate significant co-evolution as reflected in correlation ratios like mass scaling. But direct astrophysical processes linking them still need deciphering. Tracking outward movement of illuminated particles from the galactic center provides key insights. Our galaxy's supermassive black hole Sagittarius A** lies dormant currently, with only the occasional flickering pulse. But relic Fermi bubble structures reaching 25,000 light-years above and below the disk signify recent outburst activity a few million years ago. Associated shockwaves likely encouraged gravitational collapse of some hydrogen clouds into brand-new stars akin to how sonic booms shatter glass. Quasar-hosting galaxies also showcase jets triggering starbirth through compressive interactions. Observed jet-induced star formation rates exceed hundreds of new suns per year as measured in spectacular examples like Centaurus A as plasma jets inject turbulence into clouds. Compression incites rapid cooling essential for embryonic stars. Vast star-forming regions shine brightly with young hot blue stars. Outflows from accretion disks also carve out expanding bubbles in galaxies lasting tens of millions of years before dissipating. These galactic-level winds expanding at thousands of kilometers per second applies tremendous pressure that can sweep gas and dust entirely out of smaller galaxies. By regulating access to star-forming material, they indirectly govern future solar nursery patterns. Through these multitudinous mechanisms, awakened central supermassive black holes make their gravitational mark across all scales of galactic ecology, down to influencing stellar evolution pathways along directed jet paths or clearing new cavities through establishing energetic winds. Their outbursts transform galaxies. Supermassive black holes, unresolved mysteries. Despite the depth of knowledge accumulated about supermassive black holes over recent decades, major questions persist concerning their intricate relationships with host galaxies. Solving these and future puzzles relies on next-generation instruments and simulations overlapping fields from stellar physics to dark matter patterns and gravitational wave signatures. What caused such exponential expansion for early seeds to reach billion solar mass proportions within a few 100 million years after the Big Bang? Precise reconstruction requires observing signatures from primordial galaxies containing newly formed black holes. Discerning between direct collapse versus population 3 remnant models remains challenging but achievable this coming decade. We still lack complete details on accretion physics driving matter into the event horizon, particularly the innermost regions. Extreme magnetic fields likely play vital supporting roles accelerating angular momentum transport through unstable turbulent disk phases. Fully capturing complex dynamics requires computational power beyond currently available supercomputers. Outstanding theoretical issues involve galactic merger events between pairs of supermassive black holes residing in the cores of interacting galaxies. As dynamics escalate over millions of years, dual orbital motion depends sensitively on drag forces until inevitably merging. Measuring gravitational waves generated during such incidents by future detectors will expose uncharted strong field gravity. We also have yet to answer whether accretion disks can slingshot interstellar probes across intergalactic distances, enabling communications or even transportation between galaxies. While seemingly speculative now, history teaches we should not place limits on what determined civilizations may eventually achieve through harnessing natural processes. Escape velocities exceed tens of thousands of kilometers per second. Finally, we return to how shadows of black holes act as portals through which to glimpse net effects from physical laws beyond our standard models encompassing cosmic and quantum scales. What new particles or unseen forces dominate the singularity domain? Supermassive giants offer optimal testbeds for pushing known theories to their absolute limits, where we always make groundbreaking discoveries. In closing, supermassive black holes play an indispensable role governing the growth and evolution of galaxies over cosmic time. Born in the tumultuous early universe, these gravitational beasts grew rapidly through violent processes fueled by ample gas reservoirs in fledgling galaxies. At peak feeding intensity as quasars, they blaze bright enough to outshine galaxies amidst their brilliant outbursts. Their relativistic jets and blistering winds profoundly influence galactic ecology on magnificent scales. By regulating access to star-forming clouds, these processes direct stellar nursery patterns. Supermassive black holes and their host galaxies are intimately connected. When one transforms, so does the other. Yet major questions remain concerning their origins and physics underlying their most extreme behavior as they dominate local spacetime. As instruments probe deeper towards the Big Bang and theoretical models grow more sophisticated, revelations about first-generation seeds and earliest quasars now appear within reach. And monitoring gravitational waves generated during their most energetic mergers will expose hidden inner workings through strong field gravity experiments no scientist could ever hope to record in any terrestrial laboratory. The next decades promise a golden age unpacking outstanding mysteries about supermassive black holes with our galaxy serving as prime exhibit. In probing the darkness, we illuminate the universe and our own fundamental nature. As eternal cosmic witnesses, these gravitational beasts have observed the totality of our past and will watch unflinchingly deep into all our potential futures across the eons. Their truth waits patiently to be discovered. Don't forget to click subscribe if you want more weekly updates. Thanks for watching.